Hi, Fred B here, and in this video I'm going to analyze the results of my experience building the Tesla hairpin circuit. Okay, now these things have led me to some surprising conclusions, which really should have been of little surprise. Basically, everything I've found out in this so far follows regular electrical engineering practices. Okay, let me get right to it. This is a schematic for my hairpin circuit. The particular values don't really matter, and I'll explain as we get into this. And from left to right on here, we have the energy source, the mains voltage and current, which is connected to the primary of the transformer, which energizes the secondaries. These are the two coils between node A and C here in the diagram. The node B is the center tap between the two secondary coils, and in neon sign transformers this center tap is connected to the ground lug on the outside of the transformer case. It's a safety issue. But in this circuit, it was not connected and doesn't really play a role. Okay, now moving to the right, we have the spark gap. Then we have our two capacitors, which connects to the rods. We'll call them rod is located at point D and at point E. These are actually the same nodes, so they're just locating the rods. And then the load here shown would be connected in parallel with the shunt for the rods, and that shunt would go between node D and node E. That's what that line is. It's the shunt. Okay, now in order to glean an understanding of this circuit, it's helpful to simplify it. And we can take out a few of these components in one step of simplification. And we get this schematic. Now we have removed the load and removed the spark gap, which leaves us with the secondary with the unused center tap and the two capacitors in series. Now we can take this through one more step of simplification to this schematic, where the hairpin circuit is now looking a lot like your traditional tank circuit on the secondary side. And so basically it's a tank circuit on the secondary side, which is being energized from the primary through magnetic means. Now in any tank circuit, we know the resonance frequency of the circuit is dependent upon the inductance of the inductor and the capacitance of the capacitor. So now we have a very relatively simple circuit that we can look at. And now from this point right here, we can start drawing some conclusions and information about the hairpin, the behavior of the hairpin circuit. Now we know the inductance of the transformer is fixed, right? We lack the ability to adjust the inductance of the transformer. So that means the only degree of freedom here we have is to adjust the value, the capacitance in the circuit. Now the thing about neon sign transformers, and with the one I have, there's actually 3 different versions. There may be others, but there seems to be commonly 3 versions. One is the 5000 volt transformer with 120 milliamp output. We have the 10,000 volt transformer with the 60 milliamp output and the 15,000 volt transformer with the 30 millivolt output. Oops, 30 milliamp. I'm getting distracted here. I can hear my neighbors arguing with each other through my open window. Okay, so getting back to the matter at hand. What we can surmise from this is we have transformers. We can relate the inductance value of the transformers. So the 5,000 volt transformer has a relatively low inductance. We can call the 10,000 volt transformer a medium inductance and the 15,000 volt transformer high inductance. Now what does this mean with regard to the capacitance? Well, it's simple. The resonant frequency in a tank circuit is dependent upon the inductance and the capacitance in the circuit, and that inductance and that relationship is inverse. So if you have a relatively large amount of inductance, you're going to need a relatively small amount of capacitance. Well, moving on here, when I hooked up the shunt to the rods, and this is commonly reported that there is a lot of increase in the activity of the spark, the arc. You know, it goes from mild to wild. And why is that? Well, in the nature of a tank circuit, the nature of a tank circuit is it's called a tank circuit because it stores energy. You keep putting energy into it, and it keeps the voltage and the currents inside the tank circuit keep building. It's a store, a sponge for energy. So if we take the spark gap out of the circuit as our very simplified tank circuit, and we make it so it resonates at 60 hertz per second, and we energize the primary, here's a graph of the voltage that builds up in that tank circuit. You can see it builds to 70 kilovolts peak in about a quarter of a second. You know, so this is exactly why I could increase the amount of distance in the spark gap more than 2 millimeters, more than the distance that the transformer itself would only have the power, because the voltage is building up in the tank circuit to the point where it will strike an arc through a bigger spark gap than the transformer could start just by itself. But this diagram is really quite scary in that if you could 70 kilovolts is, you could pull those electrodes farther apart than 2 centimeters, and it's going to strike an arc, which means if the spark gap is open and you energize the system, something is going to overvolt, experience an overvoltage. Either the secondary windings in the transformer or the capacitors are going to burn out. Now in my case, I opened up the spark gap to only 4 millimeters, and the first thing to go, which allowed a voltage of 12,000 volts, or prevented a discharge before building up to about 12,000 volts, that was sufficient to break down the dielectric of my capacitors. So that now has become clear why the capacitors failed. because the voltage built up in the tank circuit. Alrighty, so moving on here, if we arrange the spark gap for two, if I set it at, let's just say in this transformer, the peak voltage at 5,000 volts, its operating voltage, would be 5,000 RMS volts. The peak voltage would be about 7,000 volts. So if we set the spark gap at 2.3 millimeters for 7,000 volts, here is a diagram of the voltage across the capacitors. We could say, if we go back to the original hairpin diagram, we could say this is the voltage across nodes A and C. Okay, now here's an interesting, if we set the spark gap for 20,000 volts, which would be, well, whatever that is, if it's 3,000 volts per about 7 millimeters or so, we can see here that the potential difference between across the terminals of the spark gap is going to go to 20,000 volts in about 20 milliseconds. So the potential for this tank circuit to build voltage is say extreme. Okay, now if we say for some reason the spark gap was broken, open circuited, and it was, say 4 or 5 inches, what's going to happen to the system? Well, it would be just like the tank circuit there with no spark gap at all. It would build to maximum voltage, and in this case, the particulars of my circuit, it would build up 60 to 70,000 kilovolts, 60 to 70,000 volts. So that's that's why I would imagine they have the extra safety spark gaps in Tesla coils precisely for this reason. Okay, next thing I want to talk about is the resonant peak of the circuit. With the shunt installed across the rods, which turns the hairpin into that simple tank circuit with a spark gap added on, the Q of the circuit is at its maximum when the resistance through when the rods are shorted with very low resistance path between the capacitors. Here's an image of the frequency response. This is the current through the rods as a function of frequency applied to the primary of the transformer. And you can see here it's a very sharp peak at 60 cycles per second. Now if we take that shunt off and install a load, a resistive load, and this would be as if we go back to our original diagram here, we open circuited that wire between points D and E and set the resistance of the load resistor shown in a diagram to 20,000 ohms. Now actually the diagram here is for 100,000 ohms, a load of 100,000 ohms. We can see the peak, the resonant peak has softened. This is the Q of the circuit has been reduced here. And taking this one step further, if we made the resistance of the load 1 mega ohm, then we get this for the resonant peak of the circuit, which now it's just become It's just being limited by the inductance of the transformer. So most everybody talks about how they get more power out of these things with the rods shorted. And with the rods shorted, we now know that the secondary side of the hairpin circuit forms a tank circuit which builds energy. And if we increase the resistance of the path of the tank circuit, we start dissipating energy and reducing the Q of the circuit. That's pretty clear. All right, that pretty much concludes what I have to say for this. Just in review, I've taken my experience from building my hairpin, and I looked at the schematic and saw that it could be, the hairpin circuit could be simplified and represented as a simple tank circuit that is energized from the primary of the transformer. The secondary side forms the tank circuit. That this tank circuit, without any outlet to dissipate voltage, will build substantial voltage that would short out the secondary windings of any neon sine transformer, or probably just about any capacitors you put on there. It'll build, tens of thousands of volts within tens of milliseconds. So this is quite a significant behavior to take into consideration. And something just slipped my mind. Carl Palsness, in his demonstration, he's using those doorknob capacitors. I looked them up. They are 2000 PF capacitors that are rated for 40,000 kilovolts. And I'm wondering the significance. I wonder if he figured this out too, that since those two capacitors are in series, that gives a withstand voltage of 80,000 kilovolts, and that is just sufficient to cover the voltage that my circuit simulator suggests would build up in this circuit without any way to dissipate it. So that's an interesting correlation. I'll have to contact Carl and ask him about that. Okay, I've detailed how the spark gap is the current limiting feature of the circuit, and if there's a failure of the spark gap, then the voltage buildup in the circuit will likely build up until something fails. That's why a safety spark gap is a good thing to include. Now, the thing I forgot to talk about was that the only thing that controls the resonant frequency of this device is the transformer and the amount of capacitance. That's all. The spark gap, the distance of the spark gap lacks any effect upon the resonant frequency. The amount of resistance in the path between the capacitors lacks any effect upon the frequency of the resonance. Although the resistance lowers the Q, the frequency at which the resonance is located stays the same. So that was kind of implied in what I talked about, but I wanted to state that explicitly. Okay, I think that wraps up everything I had to say about my experience with the Tesla hairpin circuit.